Okay, so 8A.3 has to do with exponential growth and decay. And the reason why we put it with what we just did is because the graphs are all actually exactly the same. The cool thing about exponential growth and decay is that people actually use it in real life. So I'm just going to read this paragraph to you. You do not have to write it all down.
I have a question.
Yes.
Is this like
So, many real-world phenomena can be modeled by functions and describe how things grow or decay as time passes. Examples of such phenomena include the studies of populations, bacteria, radioactive substances, electricity, and temperatures. So scientists use this, anthropologists and sociologists use this to study population. Biologists use this to study the growth of population in animals and plants, and, with chemicals and stuff. What I do want you to write is this part right here that defines exponential growth and decay. Any quantity that grows or decays by a fixed percentage at regular intervals is said to possess exponential growth or exponential decay. So, a graph that is decreasing is called exponential decay. So, the entire species dies. If the graph is increasing, it's called exponential growth. And that actually should make sense, right? It's decaying, meaning it's getting smaller. Growth means it's getting bigger. Okay, so something we do have to know is half-life. Half-life is the time required for a substance to decay. So half-life only has to do with decay and fall into 1/2 of its initial value, and that's what half-life is. So basically, let's say that I am studying bacteria, and I start with 100 bacteria. Okay, so let's say that I have 100 bacteria that I'm studying. The amount of time that it goes to from 100 to 50, that's called the half-life. So half-life tells us how long it takes to get to half of the amount that it currently has. Make sense? We use this for decay. We are going to be looking at formulas. Basically, and I want to tell you guys this because 4th period kind of freaked out. The formula is essentially the same every single time for growth and for decay. However, sometimes the variables change. In problems, the variable will always be defined for you. They will tell you what to plug in where. Okay? The only thing that might change is the variable that they use for the amount you started with. Sometimes it's A, and sometimes it's I. Okay? So it varies sometimes depending on who's giving the problem. They will always define it for you, but essentially it's the same. So I want to give those two right now, just so you have the generic form as well. So the formula for decay will always be, let's say y is the amount that you have after a given amount of time. Your initial amount, so I'm going to call it I for initial. Sometimes it's something different. Times 1/2 to the power of t over h. T is the amount of time that the thing is given to decay. H is the half-life. Okay? So I is your initial. It's for decay, you're always going to have initial amount times 1/2 to the amount of time over the half-life. Okay?
That's exponential form that T over H.
Mm-hmm.
Wait, what?
That looks like a cool formula. I already want to do it.
All right, guys. So formula for growth.
That's what they get for bombing from Harvard.
Growth also looks very similar. You take your initial amount. You take your initial amount, but we aren't multiplying it by 1/2. We're going to multiply it by 2. So it actually flips. To the power of t, so to the amount of time that it's given. These are generic. If a problem gives you a different formula, you just take your information and plug it in there, because sometimes we have a little bit extra information that we can plug into the formula. They will give it to you. if you are ever asked to write a formula, you will use one of these two basic forms. Okay? So let's actually look at a problem. Okay. All right. When a plant or animal dies, it stops acquiring carbon-14 from the atmosphere. So this has to do with decay. Carbon-14 decays over time with a half-life of 5,730 years. So you probably need to write that down. How much of a 10 milligram sample, so that's how much we started with, will remain after 22,920 years? So that's your time. Okay, here's the formula that they give you. Notice that it's similar to what I gave you earlier, but the variables are a little bit different. But don't fear, they tell you what the variables are. Okay, so n sub 0 is the initial amount. N is the amount remaining, so that's what we're solving for. T is the time in years, they gave us that. And H is the half-life. Okay, so like I told you, the formulas are basically the same. Exactly what I wrote down just a second ago for you. Sometimes the variables change depending on what it is we're talking about, who's giving the formula, who's doing the study. But the formula is the same. The only thing that changes occasionally are the variables. So if n sub 0 is the initial amount, how much was our initial amount? 10 milligrams. Okay, so I'm going to write that here off to the side so I know what I'm going to plug in. We don't know what the time remaining is, so that's what we're trying to solve for. What's the time in years? 22,920. And the half-life is 5,730 years. Okay? I guarantee that almost always when you plug it in, that fraction will reduce. Okay? You are allowed to use calculators. So you can use those. So let's actually plug it in. We're trying to solve for n. N sub 0 we said was 10 milligrams times 1/2 to the T over H. So that's going to be 22,920 over 5,730. So that is 10 to the 1/2. That fraction reduces to 4. It's a 4. Yeah, 22,920. Okay. Okay, so this is actually something we can do. This is 10 times, what's 1/2 to the 4th power? 1 over?
1 over 2, 4,
16. So this is 10 over 16, right? And that reduces. What does 10 over 16 reduce to? 5 over 8. Milligrams.
Where did you get 4?
It reduces.
Oh.
So growth of a town is given by the formula y equals y sub 0 times 2 to the t. Y sub 0 is your initial population. T is the time in years. Now this one is tricky because they're giving us our information a little bit differently. If there are 4,000 people after 4 years, find the initial population. So where am I plugging 4,000? To y or to y sub 0? Y0 is our initial. Do we know what the initial is? No. So where does 4,000 go? Into y. So this is going to be 4,000 equals y sub 0 times 2 to t. What is t for? Okay, so this is going to be 4,000 equals y sub 0 times what? What's 2 to the 4th? 16. And how do I get rid of that 16? Divide it. So y sub 0 equals 250. People, right? So this is what it's saying. We started with 250 people. In 4 years, that 250 people grew to 4,000 people. That's population growth. Sometimes, a lot of times, they'll still give you the initial and the time, and you have to project how many people there will be. But I wanted to show you this one so you saw a question being asked in a different way. Okay? One more. Okay, one. Okay, so here's our last one. The number of people with a flu virus is growing exponentially with time, as shown in the table below. So day 0, the very first day that the virus is detected, we have 300 people that have the virus. After 1 day, there's 600 people with the virus. And after 2 days, there's 1,200 people with the virus. What do you guys notice about the number of people? It's doubling every time, right? That's how in the formula for growth and decay we get the 2 and the 1/2. Okay? Is this a growth or a decay problem? It's growth. So we're going to use our general formula. Look back in your notes. What's the general formula for growth? Y equals I times 2 to the t. Okay, so let's take the information that we know. We don't know how many people will end up with the virus, right? Do we know how many people started? Yeah, 300. Times 2. Do we know how long that we're going to be studying the population of the virus? No. So you can leave t in the variable here. That would be your formula. That's it.
What are you trying to figure out?
They wanted us to write an equation.
Oh, okay.
This is a multiple choice. I'll scroll down in just a second as soon as you get it written down. So if you take what we have, let's scroll down. So here's the actual question and the answer choices. So we had y equals 300 times 2 to the t, right? Now the question asks you which multiple choice equation expresses the number of people having the flu at any time. Look at your answer choices, A, B, C, and D. Which one looks like the formula that we created? D. So that would be your answer choice. Okay, so decay means that the graph is decreasing. Growth means that the graph is increasing. But this is a real-world application of 8A.2. Okay.